Watching this video, what are you able to say about this pumpkin? It looks fairly unique. It's white and bumpy. It's about half the size of my head. But what's on the inside? You can't tell by looking at it. The only way you can investigate the inside of this pumpkin is if I change it, by cutting it open. Now that you can see inside, you might notice seeds and pumpkin flesh and pumpkin stringy bits. But what if you wanted to see all the seeds? You would need me to fish them out of there. What if you wanted to know the flavors or the smells? This pumpkin has been off the vine for months. What if you wanted to know what the inside of the pumpkin looked like when it was fresh? It's difficult to share all the information your audience might want by just showing the real thing. How can we improve on the real world with visualization? Now we can see the pumpkin more clearly. This visualization of the pumpkin has transparency, so we can see inside. It removes all the stringy material, and it is colored based on how flavorful the pumpkin is. This pumpkin data isn't scientifically rigorous, but it makes a valid point. Showing something as realistically as possible is not always the best goal, especially if you're trying to communicate a data-related narrative. In visualization, we have to lie to tell the truth. That is to say, realism isn't always the best way to communicate the complexity of your data. In this biological visualization, we see hundreds of ribbons floating through the structure of the proteins in this organelle. These ribbons are not a realistic representation of shapes that actually appear. They are technically a lie, but they are a meaningful simplification of strands of DNA. We used a visualization tool called VMD to analyze the hundreds of thousands of atoms in this simulation and identify which atoms were connected in patterns identifiable as DNA, then replace those atoms with ribbon geometry. Those ribbons are an abstraction of a more complex reality. In visualization, we often use abstractions to take something visually or conceptually cluttered and turn it into something meaningful for our audience. There are many ways to create abstractions. One of the most common abstractions is called a glyph. Glyphs are geometric metaphors, like the DNA ribbons. This visualization of a tornado is filled with glyphs. Arrows are a very common glyph. This visualization uses arrows on the ground to show ground wind speed. But here they also draw an analogy to grass or trees blowing in the wind. Stream tubes are another common glyph, and the orange-blue stream tubes here are tracing out the atmospheric wind direction. Balls near the center show areas of high pressure, what we associate as the actual funnel cloud of the tornado. There's also a faint gray shell around the storm, an abstraction of the storm cloud. These abstractions show us scientific information much more clearly than recorded video of a tornado. A real-world tornado is filled with dirt and fog, so it can be hard to see the inside of it. And we certainly can't tell by looking at it where changes in wind speed, temperature, and pressure occur. The tornado visualization also carefully considers how it represents all of the objects visible in the scene. In visualization, a representation is the appearance of a data object that is the result of many design choices. These four images show the exact same colliding galaxy data at the exact same moment, but they have significant differences. In the top left image, we see only stars, with colors emphasizing regions of rapid star birth. In the top right image, we still see only stars, but the motion blur is exaggerated to indicate the directions in which the stars are moving. In the bottom left, gas has been added, colored by the identity of which galaxy it originated in. And in the bottom right, the gas has been colored by its destination. Each of these representations tells a different story of the underlying data. Representations can also help cut through the noise of a busy dataset. This visualization of traffic shows the city of Chicago outlined by recognizable buildings from the downtown area. The translucent gray representation isn't distracting. The viewer's attention is drawn to the brightly colored drivers, which serves the data narrative. You can see in an earlier draft of this sequence, the buildings were shown more realistically. The visualization designers realized the shapes and locations of the buildings were familiar enough that they didn't need to include all the distracting detail of photographic textures. When designing a representation for your dataset, providing the audience with the context of the data is crucial. A visualization that omits context can lead viewers to make erroneous assumptions, and organizations trying to sell a political perspective will often intentionally obscure contextual information. For a more concrete example, this graph is called the Keeling curve. This is a fairly well-known visualization, as it provided some of the first evidence that the Earth's climate was warming. It shows a data range starting at a minimum of about 200. But why not start at 0? Well, for one, that would squash the curve so flat that the rising level of carbon dioxide would be difficult to notice. And for another, starting the y-axis at 0 would suggest that having 0 carbon dioxide in Earth's atmosphere was a reasonable scenario. This would be a misrepresentation of the meaning of the data. So whether or not it's a good idea to start the axis at 0 is dependent on the specific data set. The context of the data is that even a small change in atmospheric carbon can have a huge impact on the climate, so zooming in here makes sense. People inherently trust visualizations as authoritative sources of information. After all, they're based on data from numerical calculations, so how could they be wrong? Especially because modern audiences are not as skeptical toward visualizations as they should be, good visualizations need clarity and context. One of the best ways to provide context in a scientific visualization is to embed datasets inside each other. In this visualization, we have 3 embedded datasets. We start at a large scale in a turbulent molecular cloud, which is a common feature of most galaxies. We zoom in on a spinning disk of gas and dust called a protoplanetary disk. This is our second dataset. And as we continue to fly inward, we arrive at a third dataset of rocky planetesimals in the inner solar system. The 2 larger datasets provide context for the smaller solar system dataset. They give a sense of direction and environment, and they also provide a sense of scale, which often varies by many orders of magnitude in scientific data. Embedding datasets is useful, but it's not trivial. In addition to doubling the work you need to do reading and filtering the data, you also need to find how the 2 datasets fit together. In the process of registration, you need to unify your dataset's units of time and scale and synchronize the positions and start times of key features and events. In this visualization of a tornado-forming storm that hit Joplin, Missouri in 2011, an important element of the story was about the real city and the human lives that were affected. It was important to ensure that the tornado was placed in the correct geographic position. This is what the storm simulation looked like without context on a black background. And this is what the geospatial data looked like after registering it to the coordinates of the storm cloud simulation. Because this image was rendered from the same camera perspective as the storm cloud render, the 2 images could be layered together. This technique is especially useful if you have 2 datasets that refuse to cohabitate in the same software. The final scene not only includes the 2 sources of information registered to fit together, but uses seamless lighting and depth fog to unify the 2 data sources into one coherent picture. By bringing together advanced data and the language of cinema, visualization designers have many tools they can use to provide the all-important context for their imagery. And by rethinking their data in terms of abstractions and representations, visualization designers can avoid the clutter of the real world and get to the heart of communicating science. Fun fact: the scientists we work with often have their own abstractions for the data they create, and it's weirdly common for those abstractions to be food metaphors. Magnetic waves in the sun are bananas, a towering enzyme in a cell is a mushroom, fallen trees in the aftermath of a tornado are French fries. Recently, we were introduced to a type of pastry called a bialy that we hadn't even heard of before to describe the shape of a simulation. Now we can't work on a visualization without having a food metaphor for it.